Okay, so we'll get started. Thank you for coming. I know it's a very cold day outside, so I appreciate that you made the time to come. I will continue the discussion from last time, and then we'll start with a new topic on virtualization today, and then we'll continue with that through next class. Okay. So if you remember, just as a recap, what we were talking about last time, it was on multiprocessor and distributed scheduling. So we spent much of our time talking about this whole notion of scheduling jobs or processes that come into a system that has multiple workstations or multiple machines. And we specifically looked at the problem of when is it useful to take a job that has come to machine I and actually send it over to some other machine and execute it there. And this is broadly relates to the need to balance the load across machines and so on. Okay? And I talked about sender initiated and receiver initiated policies. I'll talk about a few case studies of actual systems that implement or have implemented these policies, so you get some flavor for what actually has been used in real systems. The first case study is a very brief case study is System V. This is a distributed operating system that was designed at Stanford. It's actually 25 years old. Okay, it's a research operating system. Never actually became a product, but nevertheless, it was one of the early ones that incorporated this idea of distributed scheduling. So in the V system, you could submit a job or start up an application or a process, and then the system would decide where to run it. Okay, whether to run it on the machine where the user typed the command or to send it somewhere else. The policy there was state change driven information policy. So what that meant was each machine would monitor its workload, and if there is any significant change in the workload, maybe the workload increases by a certain amount or reduces by a certain amount, or the queue length increases by a certain value, you would broadcast that information to everyone else, which basically says that you will tell other machines this is the new load on this on my system. Okay? So that's what is called a state change driven policy. So any significant change in CPU memory utilization was broadcast to all other nodes. Okay? The least loaded nodes, and there is a very configurable parameter M. You take the M least loaded nodes in the system, they were receiver nodes, which means they would accept requests from or jobs from other nodes, and other nodes were sender nodes. Okay? So they could offload jobs. Okay? So this was a simple sender initiated policy. If you are a sender, you would go look for a receiver, and who is a receiver depends on what load you broadcast to others. So you take the least loaded machines, and they would be your receivers, the M least loaded ones. Okay? Location policy was you look at the load table for all the machines, okay? Pick the M least values there, and then from that's your candidate list. Okay? And you don't directly send a job, you actually first probe the node and check that the load information you have is still accurate, because load can change. Okay, so you may have received some broadcasts a while ago and you just probe, and then based on whether the node is still lightly loaded or not, you will actually send the job or not send the job. So the location policy is probe a random receiver of one of those M, okay, and then if it's still receiver, transfer the job, otherwise try something else. Okay. So that's a simple instantiation of a sender initiated policy in the V system. Okay. Well, I'll talk about a different system which also did something similar. Okay. Sprite was a competing distributed operating system that was designed at Berkeley. Okay, V was designed at Stanford University. Sprite was designed at Berkeley. Sprite had many different components. It had a file system. It had distributed OS that did distributed scheduling. It implemented process migration, as we will see in the next slide as well. Okay. So the rationale for Sprite came up from this network of workstation environment. So this was around the time, late 80s, early 90s was around the time cost of machines became low enough that you could actually give each user a workstation. Workstations somewhat preceded personal computers and laptops. Today, everybody has a machine, but those days, machines were still expensive. It cost $20,000 buy a workstation, for example. But it was still a scenario where you could afford to give your users a workstation, and then you have a scenario where you have n workstations in your environment, and as you can see, workstations are still somewhat expensive. So they wanted to make sure all the resources on all the machines were somehow used. Okay. So what that meant is, if you are a user and you are not currently logged on to your machine is sitting there idle. Okay. But if there are other users in the system, they should be able to use the CPU cycles on this idling machine to run whatever jobs they want. Okay. But on the other hand, if you come back to your machine or you come to your office and you log into your machine, if there are other jobs running that you didn't start it or just sent to your machine, they should actually go back somewhere else because it's your machine. Okay? So if you are working on your machine, you should have access to it. If you're not working on your machine, the cycles are used by other machines or other users in the system. Okay? So this is workstation environment, and their philosophy was the owner of that workstation is king, in that they own the resources. When they need to use it, they get it, independent of what else is happening at that instant. Okay? So the way it would work is, the OS would monitor activity on that machine. By activity, we mean, let's say, keyboard activity or mouse activity. If your keyboard or mouse is idle, there's no keyboard input or there's no mouse input, the OS would assume that the user is not doing anything. Okay? Because if you're not typing on your machine or you're not using the mouse to do something, okay? So it assumes that the machine has become idle. Okay? Or, at least for 30 seconds, if there's no activity, would say machine has become idle. And if the number of active processes that are running is below a certain threshold, here the threshold is just the number of processors on the machine, so which means that the CPU is not actively running any jobs, then you become a receiver. Okay? So if machine is idle, the number of processes on that machine is low, you become a receiver. Okay? And then if you're a receiver, then you can actually go and try to look for work. This is a receiver initiated policy. There was a central coordinator, okay, which is tracking the load on all the machine and the state of all the machines. So you don't actually have to go and ask other machines to send you jobs. You simply tell the coordinator saying, now the machine has become a receiver. Is there a job to run? And the coordinator is tracking what else is happening on other machines, and if there is a job to run, it will be sent to that machine. Okay? And the interesting thing here was, unlike System V and some of the policies we were talking about, where you send newly arrived jobs, in Sprite you could actually take processes that are already running and move them over. Okay? So it implemented this notion of process migration, which was actually a key advance from an operating system perspective. This was still 25 years ago, actually, or a little more than that. Okay, so it's a centralized information policy, which means there's a coordinator that's tracking the load. Every machines are sending their load information, and it's specifically when you don't see any activity on your machine and the load is low, you become a receiver. You ask the coordinator, send me some work. Okay? Coordinator may say, here is a process running on some other machine, I'm going to move it over. It moves over and it resumes execution on this other machine. Okay, so that's the scheduling policy. Okay. Now the policy requires you to implement this notion of process migration, which is what we are going to talk about a little bit. We are going to come back to this, talk about it in more detail as well. Okay. So now let's say that there is a job or an application running on some machine. You want to move it to some other machine. Okay, what does that involve? What would we have to do that? Okay, so first understand what we are even trying to achieve. Okay, you understand what a process is, I presume, right? We talked about processes and threads and whatnot. The process is an application or something that's actually executing. Okay, it has resources it's consuming on the machine. We are actually talking about taking that process, okay, moving that whole process to another OS or another machine, okay, and resuming execution on that machine. That is what we are going to call process migration. Okay? And then the question is, what, from a conceptual level, not from the detail, what would we have to do to make that work? Yes, please. Okay, transfer state, something we had something, okay, new address space. Any other thoughts or comments? So you need to understand what's a process first of all. Okay, you talked about this already. Let's say that's RAM. Okay, your process may be loaded in RAM. We'll ignore that. It may be paged and so on. So process is allocated some amount of memory. Okay, so it has code, data, stack, everything is in this RAM. All of this contents have to move to the other machine. Okay? The kernel is tracking whatever this process is doing. So the process may be accessing files and whatnot. That state information also has to move. Anything that has to do with process state has to move over. Okay? What files are open? Is this actually accessing any network traffic? All the memory has to move over and so on. So essentially, what you would have to do is on this other machine, create an empty process in some sense. Okay? Move all of this over. Okay, and then basically whatever state this is the process control block which has all the state information for this process in the kernel that has to move over. And then this process has moved over and it can resume execution. Okay, this is referred to as process migration. The simple way to do it is you have to suspend the execution of the process so the memory state won't change, move it and resume execution. Okay, that's called stop and copy. You stop the process, not kill it, you just suspend it. Okay, so that its memory contents are still there and then you transfer. Okay. If you do it while it is actually executing, things become more complicated. Sprite did not do that, but that's called live migration because memory contents are changing as you transfer memory. Okay, so that's a lot more complicated process. Here, this is very simple. You're simply going to do stop and copy. And furthermore, rather than doing direct memory copy, okay, what Sprite did was it basically you has a file system that was shared. Okay, all the files on the disk were accessible everywhere. So what it simply did is rather than transferring this to memory, it simply swapped all the pages to disk, okay, and then reloaded the process here. Okay, so basically depend on the file system to facilitate the transfer. You swap everything out, send the process control block over, and just page everything back in, and the process, you have a new process on the new machine, which is just going to take over from wherever the previous process left off. Okay? Most operating systems, even today, don't actually do process migration because it's complicated. There are many details to be dealt with. Specifically, there are network level issues that have to be dealt with very carefully. Okay? Because if you have open network sockets, and you are communicating actively with other clients or other machine, if you simply move the entire process here to another machine, this machine has a different IP address. Okay, the socket connections will break if you don't do this carefully. Okay, so typically you will, if you do process migration, you have restrictions which say you can only migrate processes that don't have any network communication happening. Or if you have network communication going on, you better deal with that in some way because anything that's communicating with you doesn't know that you move. They don't expect processes to move around and the IP addresses to change. TCP cannot deal with anything like that. So you have to deal with this issue very carefully. And we will talk more about how you can deal with some of the networking aspects a little later. Sprite did not do that. Okay, so Sprite was just simply looking at processes that are bad jobs that don't they have to deal with network communication. But general process migration is difficult. Okay, so this was one of the first ones that did it. Okay, we'll come back to process migration again, but if there's any questions here, this is a good time to ask. Is it clear what process migration is? So now the reason you need this, of course, is a sender is sending his job over to a receiver. So the job is already executing. It's a process. If you want to move it, there are only two things you can do. You can kill this process and restart it from the beginning here. But then anything you have, any computation that has been done is going to be lost. The other way is you basically suspend it at its current state and move it over. Okay? That is, then you don't lose computation, but you need process migration support for it, which is complicated. So you only have these two choices with you. Okay, so Sprite decided to go down the path of you won't waste any cycles. If you actually put a process on somebody's machine, did computed for half an hour, person came back from lunch, why throw it away and restart? Let's just suspend the process and move it somewhere else and restart it. That was their philosophy. Okay? Any questions on this? Okay, so that's Sprite. The third case study is what we will call volunteer computing. Right? If I don't know if any of you have seen anything like this, so there used to be a project called SETI at home. Okay, it was a more general version of that, which is called Boink, was a project at Berkeley. Okay. What this project is supposed to do is it's called volunteer computing. Users can donate their CPU cycles for a certain project or a worthy cause. Okay, so let's say you are a researcher, okay, that needs a lot of computation for their research. Okay, let's say you are a life science researcher and you are working on cancer research and you need to analyze a lot of data for some new drug discovery. Okay? To do this kind of research, you either need an access to lots of servers and lots of computational cycles on servers, and some researchers do, and that is where they will actually run their jobs. But then if you do not have access to these resources, let's say you are not fortunate enough to have access to a very expensive large cluster, what do you do? Okay, so what you could do is you could say ask other users saying, if you have a little bit of CPU cycles to spare, can you then let me use your CPU cycles to do some of my computation? Obviously, the computation is large, so you will have to break it up into smaller pieces. And the idea is, if you are a volunteer volunteering your CPU cycles, then you contact a server saying, I am idle, send me a little bit of work, and then the server would say, here, go do this computation. You do the computation, you send the results. If you're still idle, say, go give me the next piece of work. Server will send you another piece of work. You'll do that computation, you'll send it back. Okay? So this is referred to as volunteer computing. Okay? It started with this fairly famous project called SETI at home. SETI stands for Search for Extraterrestrial Intelligence. So this was some astronomers were just trying to find intelligent life somewhere else. Okay? And what that meant was you have all these radio telescopes that are simply capturing all sorts of radio signals. And you are looking for real patterns, not noise in the signal. So a lot of the signals will have no useful information at all. It's just noise that the satellite is observing. But you have to keep sifting through lots and lots of the signals to see, do I actually see an intelligent signal in there, which could be some radio transmission from somewhere. And that was how you are actually going to find intelligent life, assuming somebody is trying to transmit some signal to you. Okay? It required a lot of horsepower. Okay? Many people may not actually even believe this is a worthy project to run. Okay, why try to look for life when you can do other, alien life when you can do other things? So, but what the researchers said is, we don't have a large cluster we can dedicate to this because nobody is going to give us so much money for this cause. But what we could do is we'll take all of the data that's coming from telescopes and ask users to deliver or volunteer their cycles. And the way they went about it in a clever way, what they did is they constructed a special screensaver. Okay, so you know what a screensaver is. If your machine is idle, the screensaver starts up. Okay? But rather than showing some nice picture, this screensaver was actually going to go and contact a server somewhere saying, send me some work. Okay? So then the server would say, here is a little bit of data from a radio telescope, go do some analysis, look for pattern. And then you do some little bit of analysis and send a yes, no answer. There's no interesting stuff here, or there is something interesting. Okay? And if your machine continues to be idle, the screensaver is going to keep doing this. Okay? And when you come back to your machine, you start working on it, the screensaver deactivates and you have your machine back. Okay, so the idea was, rather than the screensaver doing nothing useful and just showing some pretty pictures, why don't we use the CPU cycles on that machine to do something useful? Okay? So they built this model where the application was essentially running on people's machines that were volunteering CPU cycles in the form of a screensaver, okay, which would then contact the server and do all of this. And the idea was, when you come back to your machine, it's yours. We are not going to keep running things in the background and slow machines down that the users may not like and they may not participate. But if you're going for lunch, you spend an hour of your computer's time doing something useful, people are okay with that. So I think that was their philosophy. That's how they started. Then this larger project, which is called Boink, it's a Berkeley project. I forget the acronym. I think the last two are network computing, and O stands for open. I think it may be Open Internet Network Computing. So they now actually host a large number of these projects. Okay, if you are a researcher, you can go and say, here's a project, here is my data. They will basically, they go have their pool of machines and they will schedule your job as part of everyone else's job, and all these machines have been volunteered by users. So you have to go download a small app and you run it on your machine. Whenever your machine idles, it will go get some work too. Okay, so that's basically what Boeing does. Okay. So all example of volunteer computing. Right? You can think of this as some global distributed scheduler. The server is essentially scheduling jobs, and it's scheduling them across very large numbers of machines, tens or hundreds of thousands of machines across the internet. Okay? They're not really part of any cluster, they're just volunteer machines. Okay? So that's an example of distributed scheduling in the very large. Okay, questions on this? Yes. Yeah. So the question is, does process migration take place here? So this is much simpler. So you have a little bit of work, and so the idea is the work should be partitioned into small pieces that should take a relatively short period of time to do that processing. So 30 seconds, 1 minute. So since you are only spending a very little bit of time, that doesn't make sense to transfer a process. If user comes back in the middle of something, you just throw it away, and then you just assign that small data to some other machine. So you don't need to do anything complicated here. Okay. Yes?
Does the system have verifications, or how do they make sure that results are correct?
Okay, good question. So question is there any verification? How do you know that you're actually getting valid data? Yeah, because you don't know whose machine it is. It may be hacked. The user may be malicious. You send it some data, garbage comes back because user is sending some bad data back. You cannot trust anything what is happening on machine you don't know. Okay. So there is no verification happening, but they do have the ability to send the same piece of data to multiple independent machines, and if all of them say the same thing, then you vote and say, okay, everybody agrees. These are completely independent machines, so it's unlikely that the same malicious user has taken over all of those three machines and sending the same bad result back. So you can do verification just by redundancy across independent machines. So even if one machine sends some bad data, you can run the same computation elsewhere and verify. So you can do that at least. Any other questions here? Yeah.
Even the process could be malicious, which the user, the volunteer is running. So how does the volunteer verify to whom he is volunteering?
Okay. Question is how does the volunteer know what is actually running on their machine? So this is a good point. So you have to trust whoever you have given your machine access to. If you believe that these entities are malicious, then you shouldn't do it at all. So the idea here is that you have downloaded application from an application, some server, that you have some level of trust and are sort of willing to relate to that cause, and you assume that they are not going to do something bad. So you have put a little bit of trust here. You are absolutely right. If you do not trust someone and say, here, take my machine, do whatever you want, then you will have criminals taking over your machine and doing arbitrarily bad things. You don't want that to happen. Okay, so when you do this, you are assuming a level of trust between the user and whoever is sending jobs. That trust doesn't exist. You can't have completely untrusted person sending computation and untrusted machines taking that. That won't work in this world. Okay. Any other questions here? Okay, so we will continue on to the fourth case study, which is a system called Condor. This is a system that was or is still being developed at the University of Wisconsin. This was developed as a distributed cluster scheduler. Okay? And the idea was very similar to whatever happened in Sprite, where you had idle cycles on a set of machines on a LAN, and you want to make use of those idle cycles. So this is, think of this as a mix of whatever volunteer computing is doing, but within a department. You're not going out to the internet and asking for users. So maybe you have 10 machines in your lab, in your research lab. Okay? 10 users, you know one another, and you want to use machines that belong to your friends within your lab or other friends in the department, and you do exactly what was happening on SETI at home or volunteer computing. There will be a batch scheduler. You submit jobs to that scheduler. The batch scheduler waits until any of the machines in that local environment becomes idle, and when it becomes idle, it sends it a job. Okay? When the user comes back, the job has to either stop and restart it somewhere else, or terminated and restarted from the beginning. That depends on what policy you implemented. So Condor allows you to take some machines within a department or an organization, or just machines that a set of people have come together with, and essentially schedule jobs on those machines as if they were a cluster of servers. You can also run Condor on real servers where you're not donating cycles. These are machines just simply dedicated to running jobs. So it's essentially a scheduler that can accept a set of jobs that are being sent to it, and they get scheduled onto machines that are either being made available dynamically or statically configured in a pool. Okay? So it's a project that's used by many different clusters at many different environments, and you have the same kinds of philosophy you will see in Sprite, saying if a user returns to the workstation, you have to suspend whatever was running there. And then you can't have background load slowing down a user's machine that they have donated to the same policy. And there are variants of Condor that will support process migration. For that, you have to ensure that all machines are homogeneous. If you have some Windows machines and some Linux machine, you can't do process migration. You can't migrate a process from one OS to another. You need to assume that it's homogeneous. Okay. So under certain restricted scenarios, you can do process migration, but when you have heterogeneity, the simple strategy is if you have unfinished jobs, you just kill them and restart the job somewhere else. That's a safer approach. It works even though the platforms may not be exactly the same. Okay, so that's Condor. There are many similar systems that you will actually see today, like Condor. There is one called Sun Grid Engine, or SGE, that is actually used in a cluster in this department. There is a cluster called Swarm, which anyone can get access to if they have a project that requires jobs to run on lots of machines. And the way you actually run computation there is you don't log, so that's a cluster with more than 100 servers. You don't log into an individual server and start a job. You log into a master machine and just submit your job, and then this job scheduler decides which of the servers in the pool will actually run the job. So it will wait for an idle server and then send your job there, or you may have lots of jobs. It will just send them to idling servers, and then they will run the job and send back results and so. Okay, very similar techniques are used in these other systems. I won't go into them. Just be aware that there are lots of distributed schedulers. Yeah, so this is essentially how the concept of distributed scheduling that we started with is actually being used today to submit jobs that are either being sent to machines that users have donated for whenever they are not using them, you run jobs on, or you have an actual dedicated pool of servers and there is a queue, and the distributed scheduler is simply farming out jobs to individual servers. And that's how most of these actually work today. Right? Anyone use Sun Grid Engine? A few of you. Okay, so we will continue. So this is going to be now a change to the next topic. So let me just pause here and say, are there any questions on distributed scheduling? We are going to start talking about virtualization next. Anything at all before I move on? Okay. So next topic, which is still part of our discussion of processes and threads and whatnot, is on virtualization. Okay, so what we will do today is I'll talk about what it is. Okay, and you will see that there are different types of virtualization, and we'll start talking about a specific one called hardware virtualization. Okay, next time we'll talk about OS virtualization. Okay, so let's start with what is virtualization. So here's the definition, very broad definition. You may have used virtualization before in various forms. It will all map onto this definition, even though it may not be apparent why this definition has anything to do with what you may understand of virtualization. So virtualization simply means you can extend or replace one interface that mimics the behavior of another interface. Okay, let me show you an example to sort of make this a little more clear. So here is a picture that shows you system A, which runs some hardware and some software. Okay, what that hardware and software is at this point is not important. It could be just an OS, it could be an application, it doesn't matter. and it exposes a certain interface. Okay? And then there are programs that are using that interface to implement some functionality. And that's a typical system. You could have software system A could be an OS program, could be user program. Interface A would be the system call interface that the OS is exporting. As an example, that's just not the only way to do it. Okay? And here is another system. This is system B. Okay? It is running a hardware and another system, okay, which exposes a different interface B. Okay? Now, since this interface is different, it should be clear that if you just take this program and run it here, it will not run because it was designed for a different API. Clearly, if you change the API, your program will break. It's not going to run. Okay? Now, if you actually take interface B and write a layer of software on top of it, which takes interface B and mimics interface A using B, okay, then you can take that original program and run it here, because now that layer has actually exposed to you interface A, except that the interface A is actually implemented internally by mapping it to a different API. You're using one API to mimic another API. Okay? This is what we will call virtualization. Okay? Is the ability to extend or replace an existing interface to mimic the behavior of another interface or another system. Okay? And we'll go into details of what the interfaces are, why are you mimicking, what are you mimicking, how do you mimic, all that we'll talk about. But let me start with a little bit of history. Okay, so this virtualization technologies are actually quite old. They were designed in the 70s. Even before distributed systems became popular, virtualization technologies were already in place. Okay, and this was actually designed by IBM for their mainframe systems back in the old days. Okay? And the reason they had to implement virtualization was following. I mean, mainframes are expensive, and they were expensive 30 years ago, as it cost millions of dollars to buy a large mainframe computer. Okay? So let's say you are a large company that's invested a lot of money and bought a mainframe to run some high-end applications. Okay? Few years go by, machine becomes old. You go back to whoever manufactured your mainframe and go and ask to buy a new machine. Okay? Let's say the company is IBM that's selling you this machine. Then IBM says, we have now a new version of the mainframe, much better than the one you have. Maybe it also costs a lot of money, but it can do lots of things. It can do it faster, and so on. Let's say, by the way, in 5 years, things have changed. We have new OS, we have new architecture, so none of your old programs are going to work. Okay? So if you are a company that spent $1 million a few years ago and built all sorts of applications, now you want to replace the hardware, and your vendor says, oh, by the way, we have a really great new machine, but nothing that you have is ever going to run on it. That's not something you want to hear, because then you have to go and report all of your application onto this new platform. Okay? So, and you probably spent a lot of resources as your company building these applications, and you don't want to disrupt that and whatnot. But if you look at how hardware and software evolves, architectures change, OSs change, and in those days, technology evolution was such that every few years you come up with a new family of processors that was faster, better, instruction sets changed, you come up with a new OS. So this was actually the case. If you buy something and 6 years out, you go out, you can't buy something that will look exactly the same, as just faster, because things were not standardized. Okay? So IBM clearly knew that if you say that, your customers will never buy anything from you. But they decided, why not say the same thing but do that? We're saying, we'll sell you a new piece of hardware. It's going to cost you a lot of money. So everything will run faster, better. And by the way, everything you ran previously will run intact, even though everything underneath has changed. The OS is different, CPU is different, but don't worry. You can just take your code, run it here, and it will run. A much better way to sell machines, because our customers say, okay, I buy a faster machine, I don't have to do anything, just move my code and data and everything runs as is, right? So, but in order to say something like that, what you had to do is, if you actually change the hardware, CPU, OS, you had to put a virtualization layer on top, so that any application that was designed to run an old machine, expected an old interface, could still run on this new machine, even though the actual native interface on the machine is completely different, right? So you essentially have to put an emulation layer. So if you write new applications, you have a choice. You can write it to the new interface, so it will run natively, or you can still use the old interface if that's what you're familiar with. But old applications shouldn't stop running. Okay, so this is why IBM in those days invented virtualization technologies, because their new generations of mainframes did have this problem, and you didn't want to tell your new customer saying you can't run your code. That's not what they want to hear. So they said we will write a layer for you. It will mimic an interface, so your applications will look like, I assume that they're still running on old machines, even though it's actually running on a completely new machine. Okay. So this is the history behind it. Okay, and then this is for a long time was the only use of virtualization and then late 90s, early 2000s, this technology became useful for lots of other useful things that you probably are seeing today, which we will talk about. Okay, but this is the history, and this is why we say it is extending or replacing an interface, and it mimics the behavior of another system or another interface. So essentially, all of virtualization technology will be a layer that provides an abstraction. The abstraction is basically going to provide an interface that's not the native interface. You are going to fake something else. Okay, so the application that was designed to run on some other kind of environment will run in a different environment altogether, not knowing that the actual environment on that machine is not the same as what it was designed to run on. Okay? Any questions on this? Okay, so now we'll talk about what are these interfaces and what can you mimic. So there are different interfaces that you will see in any given machine. Okay? You can have the hardware level interface. In this case, the interface is what CPU and what instruction set is it running. Is it an Intel machine? Is it a Power PC? Is it a RISC architecture, CISC architecture? That's your hardware level interface. Okay? You can have an OS level interface, which is it Windows? Is it Linux? Is it Mac? Which version of Windows is it? Is it some other operating system? That's your OS level interface. Okay. You can have application level interfaces, which is this designed to, is this a C program that's going to run on the C library, some other Python program that requires a Python interface and so on. So application level interface. So you have different interfaces in any given system, all the way from hardware to applications. Now you can implement virtualization at any of those layers. You can take any level of that interface and mimic some other interface with it. You can take one hardware and mimic another hardware. You can take one OS, mimic another OS. You can take one application level interface and mimic it with another application level interface. So in other words, what you have to realize is you can implement virtualization at different levels. And depending on what level you implement it, you will have that level of virtualization. So you can have hardware virtualization, you can have OS level virtualization, or application level virtualization. Okay? So when you hear the word virtualization, it's not just one thing. It depends on what level is it implemented in and what interface is it actually emulating. And depending on that, you're going to get different types of virtualization. And we'll look at all of them, okay, at different levels of detail. Okay, so depending on what is replaced and what is mimicked, we are going to get different levels. Today we are going to talk about hardware level virtualization. Okay? We may not finish that, so we'll have some overflow into next time, but also next time we'll talk about OS level. Okay? Application level, I won't talk about a whole lot, just mention it briefly. You probably have seen application level virtualization without realizing it a whole lot. Example of application level virtualization is JVM. The Java code is actually application level virtualization. It runs on Java virtual machine. Okay? Java JVM emulates an abstract machine, not any, but it uses a native machine to emulate an abstract Java virtual machine that's defined in the Java spec. Okay? Once you write Java code, it doesn't matter whether it's running on a JVM, on Windows JVM, on some other platform, it's going to run the same way, because JVM is emulating whatever OS is exposing to it on that environment and exposing a Java virtual machine abstraction. Okay, so that's an application level virtualization. All of that is sort of being done in a library, or in this case, a JVM. Okay, so we will come back to this, but that's one level of virtualization you've seen already. Okay, but we'll talk more about hardware virtualization. Any questions here? Okay, so I'm going to go through a few different types of hardware virtualization first, and then we will go and look at a certain subset of this in a lot more detail. Okay? This very basic form or way to implement hardware level virtualization is called emulation or full emulation. Okay? What happens in a full emulation is you basically have a program. Okay? So that's in software emulating a different type of hardware altogether. Okay? Simple way to think about this is you have a program that emulates in software all the functionality of a PC, of a personal computer. Okay, in this case, the software is going to emulate an Intel architecture PC. Okay? Then any program that runs on any OS that runs on that emulated layer is going to look at that PC and assume that that's actually a real PC, although it's an emulation of a PC. It's a software implementation of a personal computer. Okay? And you can use this. This is a very general form of virtualization, but you can emulate on any platform, any other kind of platform. You can run on a Mac and emulate some other machine, or you can run on a different architecture altogether and emulate a PC and so on. Okay? And there are many examples of this, some of which you may have actually heard of. There's one called Box, which is a project that you can, open source project, and download it and run it. There is one called QEMU, which is very related to Box, and there's another one called Virtual PC for the Mac. I'm going to explain that in a little more detail. Okay? So Virtual PC for Mac was actually a product, no longer existing product, but a former product from Microsoft. Okay? Now, maybe 5 years ago, Apple made a transition to using Intel processors for their Macs. Before that, they used to run on PowerPC processors, completely different processor family. Okay? So if you have a PowerPC based Mac or had a PowerPC based Mac, you couldn't run any Windows applications or any applications that were designed for Intel machine. Windows is also always designed for Intel architectures. Okay? So what Microsoft did at that point is they came up with this product called Virtual PC, and as the name suggests, what this product did is emulated an Intel PC. Okay? Product ran on PowerPC Macs, but it emulated an Intel PC. It basically in software emulated a processor, emulated the instruction set for the processor, it emulated the PCI bus, it emulated all the hardware that you actually find on a PC. Okay? And now if you have a software implementation of a PC, you could actually run any operating system that runs on a normal PC. In other words, you could actually run Windows on that virtual PC. So you would have Mac OS, okay, which is PowerPC based, not Intel based. And then you have a software implementation of, draw a picture here. So you have a software implementation of PC and you're running Windows in it. And that is a useful thing for many. So here is your Mac. Okay. So it's PowerPC CPU. Okay. This is OS X that's designed to run on PowerPC CPU. This is your virtual PC. This is emulating an i86 CPU. And then all of the hardware that you see on the Mac. So this is a software implementation. It's an emulator that is emulating a PC. So now if you have this, you can then run Windows or you can run Linux here, and then you can run Windows apps. So they were essentially selling virtual PC as a way to run Microsoft Office on a Mac, because in those days you actually did not have a native implementation of Office. So if you wanted to do PowerPoint or Word, you would either have to go get a Windows PC and do it, or you have to buy virtual PC and install Windows inside that virtual PC and then run Windows and whatever apps you run, including Office. Okay. So now the important thing here is this layer here, the virtual PC layer, is essentially emulating an i86 instruction set using a PowerPC instruction set. What that means is when a program runs here, and this is an Intel program that's compiled to an Intel architecture, it is going to execute Intel-based assembly instruction, i86 assembly instruction. Each assembly instruction has to be natively translated. If you run the add instruction in Intel, you have to then translate it to something equivalent on PowerPC and actually execute that so that whatever you are executing actually takes place there. Okay, do you understand what I'm saying? So you have to essentially translate, think of it as translating assembly instruction by assembly instruction. Each assembly instruction that you actually execute here has to be translated into one or more equivalent set of instructions that do the same thing on the native architecture. Okay, so you're essentially doing it like a language translation. Somebody speaks in one language, you're translating word for word in another language, so you can talk to one another. Same thing. You're doing translation. Okay. So this, needless to say, is going to be very slow, okay, because you're taking each instruction and natively doing sort of mapping it to some other instruction and executing that. This is how the application is actually going to run. Okay, is that clear? So now the technique is general enough that you can write whatever emulators you want. Here your PowerPC, you can write another emulator that emulates whatever other machine you want. And then you can run any OS designed to run on that machine, for example. So emulation, in other words, is a very general concept or general way to do virtualization. It is slow, but it's doing literal translation. Okay, so you can emulate any CPU using any other CPU. Okay, is that clear? Yes, question.
So here we need to take care about the registers and
Yes.
32-bit, 64.
Yes, so you will need to actually implement registers in software. You have to actually have all of that in there, right? So there may be some number of registers. So your registers will be actually memory addresses. If you manipulate registers, you'll do something using actual registers, for example. So all of that, you have to actually emulate everything that you see on a Intel machine in this case and implement it using Power. So that's why I said it's going to be slow, but you can certainly do it. Okay? Yes, Patrick.
Is it much more difficult to emulate a RISC architecture on top of the system?
Okay. Question: is it difficult to emulate a RISC architecture with CISC? Not quite. You can emulate any architecture with any other architecture because these are all at some level. All the processors map onto von Neumann machine, so you can run any program on them. It's just a matter of how efficient your implementation is. The instruction set is different. Right? So you will have, if you have a RISC instruction set, you're doing something, you have to map it onto something equivalent that you can do with a CISC instruction set, for example. Right? So I don't think it's more complicated or not, it's just an efficiency issue. This is similar to asking, is it easier to translate from French to English or Spanish to English? I mean, they are both translations.
Well, if you're saying like something like, so say in that context, if you in one language, if you say a bunch of things with one word,
Yes.
and then so that's your underlying.
Yes. So you may have to translate. So what you are simply saying is one instruction here may be a set of instructions underneath.
Right.
So that will just impose a certain penalty because it depends on how rich the underlying interface is. If the underlying interface is simpler, you will need more instructions or more calls to emulate the same one instruction in the one thing you're trying to emulate. Okay, that will really depend on what you're trying to emulate and how rich the underlying interface is. It can be done. Some will be more complex or more inefficient than others. That's all. Okay. Yes.
Can we emulate a 64-bit system on 32-bit?
Can you emulate a 64-bit system on 32-bit? You probably can, but it's going to also take some overhead because 32-bit essentially will be built in a certain way. If you're 64-bit words and you're doing 64-bit computation, if you do a 64-bit add and your 32-bit adds, you have to somehow map it and do multiple adds and merge the results and so on. You can indeed do it. It's going to just be more inefficient to do it. That's all.
And in the opposite context from what he said, if there are multiple instructions in the system that you're trying to emulate, that can be translated to a single instruction in the hardware. Is that possible? Or
Multiple instructions in the interface here is translated to a single instruction. Then you may be able to do that too, but typically when you are running, you have to do one instruction at a time because the emulated CPU is executing an instruction. Okay? To execute it, you have to map it to something. You can't say, what are your next 3 instructions? I'm going to take all of them. That's not how CPUs execute because this is a emulated CPU. So it is going to have an instruction pointer. It will take an instruction and try to run it. So that is what has to be mapped.
so it is always less efficient.
Yeah, so you will have to have one instruction here map onto either one or more. You can't take 3 instructions and map because the CPU doesn't execute 3 instructions at once. Okay, just based on how you're doing the translation. Okay, any other questions? So that's emulation. So here you can take any architecture and map it, and at hardware level map it to any other architecture. The next one is what we will call full or native virtualization. Okay, so here there's an important difference between emulation and full virtualization. This is also at the hardware level. The only difference is you are using the same interface to emulate the same interface again in the virtual layer. Okay? So in other words, the emulated interface and the native interface are one and the same in case of full virtualization. So going back here, interface A and interface B, same interfaces. They're not different. That is what full virtualization means. Okay, so in this case, so you are going to emulate i86 on i86, for example. Okay, so the mapping is going to be much easier because the emulated instruction set and the underlying instruction set are one and the same. Okay, if you say add that, there's a native instruction that does exactly the same thing. So you don't have to do too much translation. So needless to say, it's going to be a lot more efficient if you're trying to emulate the same interface inside your virtualization layer as the native interface. Okay. So now you can ask the question, so why would you ever do that? Why would you actually emulate one interface which is the same as the native interface? Okay. Yes, you have something to say or you would comment on it? Or no, you can answer the question, that's fine.
So it's a segment the system, the machine, logically different machines for security.
Okay. So you may need this for any number of reasons. Okay. So one scenario was mentioned is something about security and slicing the machine. So I'll give you several use cases, right? So one use case is, although the interface is the same, the operating systems don't have to be the same. Okay? You can run Windows on Linux. Right? So to run Windows on Linux, your Linux runs on a PC. Okay? You create a virtual machine that also emulates an Intel PC, but you run Windows in there, for example. Right? You can run a different operating system. Common use case. Okay? In both cases, you need to have the same underlying architecture. Okay? So there's still a utility to doing this. You can run an old version of the OS. You can even run Linux on Linux. This is just an older OS, and this newer OS. The application cannot be ported to a new version because it's running on old APIs. Okay? Just same mainframe example. Okay? You can basically emulate the same architecture, but the OS that is running is the older version and the app is using the older interface. Another example. Okay? You can use it if you use VirtualBox, VMware, Parallels. That's the same scenario where you run on an Intel machine. The virtual machine is also emulating another Intel machine. You use it for doing testing, development, any of these things. Right? So your test machine is just you run something inside a virtual machine for testing purposes, for example. Okay. The example that Patrick gave was an example on servers where the reason you may do this is I only showed one picture, but there's nothing that prevents you from running more than one virtual machine in this case. Okay, they will all have the same emulation and they can run multiple OSs. Is often the case in servers. If you have a 16-core server, you don't need all 16 cores for a single application. You slice it into smaller virtual machine. Each virtual machine gets some smaller number of cores, let's say 2 of the 16 cores, and then you run a smaller applications on those virtual machines. Each application is isolated from other applications. So it's like you took a larger server and sliced it into 8 smaller servers. Each is running inside a virtual machine. Okay? You don't need to emulate a new hardware interface. The same interface, just that you're partitioning resources. Okay? So there are any number of reasons why you may want your virtualization layer to actually emulate the same as the native interface. And you can use this in many useful ways. Yeah, so as I said, this is going to be more efficient than emulation because the translation is one-to-one. You'll basically be able to translate much more efficiently. And there are a number of products that do this. Some of you have played with. VirtualBox is an open source product. There's VMware Workstation, there's Parallels. IBM has its VM family that you do the same thing on mainframes. Mainframes, you may have 1024 cores. You don't need one application to run there. You carve it out into smaller machines and run applications into smaller virtual machines. Okay. All right. So there are several other examples of that I'm going to talk about. There's one called para-virtualization. I'm going to come back to that. Okay, in para-virtualization, you are going to emulate the same interface, except that you are going to actually make modifications to the code that's running inside the virtual machine. I'll talk about why that is needed. Until now, we have assumed that so long as the virtualization layer is built properly, whatever is running inside runs unmodified from its old environment. It's running in a new environment unmodified. But if you are allowed to change the code, we can actually do things more efficiently. I will talk a little bit about that after I present some other slides. We'll come back to this. Okay? That's called para-virtualization. It's an optimization on full virtualization. You can also do this at the OS level. Okay? You can have the OS interface. So until now, we are talking about emulating one instruction set using another instruction set. See, one CPU instruction set using another CPU instruction set. Okay, now if you go one level up the stack, you can use one system call interface to emulate another system call interface. That would be referred to as OS level virtualization. Okay, so there are many examples of OS level virtualization as well. And so this also allows you to take a machine, carve it up into smaller virtual servers, and run an application isolated inside a virtual server. It doesn't see what's happening in other virtual servers on the same environment. Okay? Each gets a view of the OS that is being emulated. Okay? There are many examples of this. Again, we'll come back to this on Monday and we'll talk about this in more details. Solaris Containers, which is Solaris's product that does implementation of OS level virtualization. It even allows you to have an old version of the kernel being exposed by a newer version, just so that you don't even have to port your application because the system call changed and the application broke. Right? They designed it for exactly the same reason IBM designed its virtualization products. You could take a big machine, partition it into smaller machine, or you could take code that was written on the previous version of the OS. No porting needed. You simply start it in a container and say, the container should emulate the previous version of the OS. So the OS kernel would then accept older system calls that it natively doesn't accept, and it does the translation. That is Solaris container. In BSD, you have this notion of jails. Linux containers are actually now actively under development. There used to be something called vServers. Now there's something called Linux containers, which I'll talk about as well. There are other products like Docker. If you've heard of them, they use OS level virtualization. Okay. Application level virtualization, I said, is now doing this emulation at the application level. Okay, you basically take one library interface and you emulate another library interface. Okay. There are many examples of this. Okay. JVM I already mentioned. Okay. There are two other examples. There's one called Wine. If you probably have seen Wine, you may know what that is. So Wine is an implementation of the Win32 API. Win32 is Microsoft native API on which Windows programs run. Yeah, Wine itself runs on many different platforms. You can get Wine on a Mac, you can get Wine on Linux, and if you implement Wine, you can run Windows applications on top of Wine, because Windows applications are going to make Win32 calls. Wine simply takes those Win32 calls and maps them into whatever low-level library calls are needed to implement those calls. So it's a re-implementation of Win32 API using some other platforms, libraries, and APIs. Okay, so that's application level virtualization. Okay. Another one here called Rosetta, which was actually product on the Mac. It's now no longer available. But when Apple rather made the transition from PowerPC to Intel architectures, there were a lot of applications that were already developed for PowerPC. Okay? So now you go out, buy a new Mac. You don't have to say, okay, now all my applications stop running because the instruction set is different. Okay? So that would obviously have happened. But what Apple did is they shipped this technology called Rosetta. Okay? That came with your new Mac. Okay? You could just simply put a PowerPC application on your Intel Mac and just start it and it would just run. Okay? No change needed at all. And what was happening is the OS would recognize that this is not a natively built application. It's designed for PowerPC. Okay? And it would run on the Rosetta translation layer. What Rosetta would do is it would do instruction set translation. It would take a PowerPC instruction that was being executed, transparently map it to an Intel instruction. Okay, so your code would run unmodified and you wouldn't even see what was going on. You did not even need to run a virtual machine. They shipped Rosetta as a library that automatically attached itself whenever you started a PowerPC machine application. Okay. So this was actually a good way to transition when you're changing all the hardware underneath. Your users are not going to be happy if they have bought lots of application, they can't just run it. They have to go out buy new applications. So they made the transition very seamless. Okay. So same thing happens at hardware level where we did native translation. This was just an implementation that shipped as a library, just so that you didn't have to. They could have said, I mean, create a virtual machine, run your PowerPC apps in a virtual machine. It's more clunky. Okay, they just said you just transfer all the code and just start the application. It will just run. Okay, much more seamless to the user. Okay, clever use of virtualization technology. Okay. So that's application level. We'll come back to a little bit of that also. Okay. So now we'll go back to hardware level virtualization and do a little more deep dive into it and see how things work. Okay. So these two pictures show you the two very common ways to do hardware level virtualization. Okay. The virtualization layer, okay, which I have been calling virtualization layer, actually has a name. Okay. It is either called a virtual machine monitor or a hypervisor. Okay. So if you hear the term hypervisor, you should immediately think that's the layer, that's software layer that's doing the virtualization for you. Okay. And you will see that there are two types of hypervisor, two ways to implement hardware level virtualization. There's something called type 1 and type 2. Very odd use of name, they just numbered them, but that's what they call them. So type 1 virtualization is also referred to as bare metal virtualization. Okay. What happens if you have a type 1 hypervisor is you take your machine, okay, you don't install an OS on that machine, you simply install an hypervisor. The hypervisor acts like a tiny OS kernel, but it's actually built only to provide virtualization services. Okay? So it's basically, think of it as a customized kernel that's simply designed to only do virtualization, nothing else. So you directly boot the hypervisor on your machine rather than booting an OS and then running some virtualization on top of it. Okay? This is called type 1 hypervisor. Okay? Here is type 2 hypervisor. This is what you may be familiar with if you use VirtualBox and so on. A type 2 hypervisor actually runs on a real operating system. A real operating system is called the host operating system. So you have an actual OS running on your machine, which we'll call the host. Okay? Then you start a virtualization product which implements a type 2 hypervisor. And that hypervisor presents a virtual machine abstraction. It's the same interface it's exposing. And then you run another OS inside that virtual machine. Okay? So that OS is called a guest operating system. This is called the host operating system. So you basically have type 2 hypervisors cannot run by themselves on the machine. You can't boot a type 2 hypervisor. You actually have to boot a machine with a real OS and then run type 2 hypervisors inside that OS. Okay. VMware Workstation, Parallel, VirtualBox, they all do type 2 virtualization. Okay, type 2 hypervisor. The type 1 hypervisors are really used in server environments. They're really used to partition the machine into smaller virtual machines and run either different applications, different operating systems and whatnot. What is shown here is a server that runs type 1 hypervisor is two virtual machines. One is running Windows and your Windows apps, another one is running Linux apps, and there may be more. Okay. So type 1 you will only see in server environments. You typically won't run a type 1 hypervisor on your PC or laptop. Okay, you can, but you typically won't. You will use something like that in your desktop environment. Okay. Both do the same thing. Okay. They are going to take the native interface and emulate, in most cases, the same interface on top, because we are saying we are going to expose the same interface and we'll use that interface to construct virtual machines and run operating systems inside them and applications. Okay, is that clear? Any questions? Yes.
So you can install two operating system in your PC, for example, Linux and Windows. Is it using the type 1 hypervisor?
Okay. Question is, you can install multiple operating systems on your PC. Is that using virtualization? Okay. So there are many ways to run operating systems on a machine. A simple way is called a dual boot environment, where you take your disk, you partition it into two parts, install Windows on one and Linux on the other, and when boot time you simply pick one or the other. Okay? That's not using any virtualization at all. It's simply telling your BIOS saying boot from this kernel or boot from that kernel. And no virtualization, just simply OS is running natively. That's not virtualization. If you are actually using virtualization, typically on a PC you will use this, where you will boot up your machine. Then you will start a virtual machine product. A virtual machine product will expose a virtual machine, and then you will actually boot another OS in there. Right? So you have Windows running and Linux running at the same time, or Mac running and something else running at the same time. That is virtualization. Virtualization is not the same as dual boot. Okay, that's a different technique altogether, not using any virtualization. That's simply picking which OS to boot from. So you have just installed multiple OSs on your disk. That's all there is to it. Okay? Next question.
Is Bootcamp an OS X type one?
Yes, Boot Camp is actually just a dual boot environment. It's not using any virtualization.
Even to run Windows on OS X hardware, you don't need any.
No, Boot Camp is simply the same thing what he was asking. You just take your disk, you partition it, you install Windows in one partition, Linux in the other, and then at boot time you just get to pick which kernel to boot from. You just give a choice of kernels. It's just a disk with multiple operating systems installed on it. No virtualization being used. Okay. Any other questions here? Okay. All right. So that's hypervisors. I'm going to talk a little bit about how virtualization is going to work, specifically in type 1 virtualization. It requires a little bit of background into how hardware architectures work and so on. Now, if you take any CPU in general, you will see that it has multiple what are called security modes or protection modes, as they are called. Okay? And a protection mode basically gives different levels of privileges to whatever is executing in that mode. Okay? Most CPUs will at least have two protection modes, something called a user mode and a kernel mode. Okay? When a user application process is running, the CPU is set to user mode. And when the OS kernel is running on the CPU mode is set to kernel mode. Okay? And the question is, what's the difference between user mode and kernel mode? So if you take your instructions that your CPU supports, okay, you will label them as either user mode instructions or kernel mode instructions. If you're running in user mode, your program can only execute user mode instruction. If it tries to execute a kernel mode instruction, it will give an error and the program will be terminated by hardware. So you do not have enough rights to do this. Okay? On the other hand, if you are in kernel mode, all instructions can be executed. Typically, only the kernel is executing in kernel mode. Okay? And the reason for this is kernel is more trusted than users application. Okay? There may be some assembly instructions you don't want to give direct access to an application process. Okay? There are many such, but take the halt instruction, for example. Halt simply halts the CPU. If you let an arbitrary application just issue halt, everything will stop. Whether that is malicious or not is a different matter. You don't want the application process to simply go and halt the CPU. You want the OS to shut down the machine. Okay? So you will not allow a user process to issue an instruction. If it does, it will basically get a trap and say you don't have rights to do this. Okay, the way hardware is actually going to enforce that is simply going to say, of all the instruction, label them. This is the hardware designer is going to label each instruction user mode, kernel mode. And then when the process is running, the CPU mode will be set to one of these two. Yeah, and if you try to execute a kernel mode instruction from user mode, you won't be allowed to. Kernel mode, everything is allowed. Okay? So these are called protection levels. Okay? So typically every CPU will have at least two, and this is meant to protect OS and have it do its thing and not allow users applications to do arbitrarily bad things and whatnot. Okay, but there may be more than two. Okay? So in the Intel architecture, you can have up to 4. There's something called ring 0, ring 1, ring 2, ring 3. Ring 0 is same as kernel mode, everything is allowed. Ring 3 is user mode, only some restricted set of instructions are allowed, others are not allowed. Okay? So, so that's one concept to keep in mind. You know, so there are some set of instructions that can only be executed in kernel mode. Many of these have to do with I/O instructions. They have to do instructions that change page tables and whatnot, because you don't want applications to do this. Only kernel is allowed to do this. Okay? So we'll call these sensitive instructions. Okay? These are kernel mode instructions. Okay? And now there are separate set of instructions within an instruction set that are also going to cause a trap. Okay? If you do divide by 0, application gets a trap saying that's not allowed. Okay, you try to follow a null pointer, you're going to get a trap because that you can't actually dereference a null pointer or a bad pointer, or you can get a segmentation fault and so on. Okay, so there are instructions that are going to also cause traps, which are going to be called privileged instructions, and there are some instructions that do this in kernel mode as well. Okay. So now I will state a result, and then we'll talk about why that result is true. So if you have type 1 virtualization, which is bare metal hypervisors, okay, type 1 virtualization can be implemented or is feasible only if your sensitive instructions, which are your kernel mode instructions, are also privileged instructions, which means every instruction in the kernel mode also causes a trap. If you have this property, if your CPU enforces this property, only then can you implement type 1 virtualization. Okay. Why that is, I will talk about in just a moment, but first try to understand what I'm even trying to say. Okay. So bare metal hypervisors can only be implemented on those CPUs where your sensitive instructions, which are those kernel mode instructions, also cause a trap whenever they're executed, okay, which are also called privileged instructions. Okay. If your CPU doesn't do that, then you cannot implement type 1 hypervisors at all. Okay. In particular, okay, Intel 386 and all of the following processor architecture sets that came from Intel CPUs actually ignore sensitive instructions in user mode. Okay. Which means rather, so if you actually have a sensitive user application, you do halt. In this case, you are not actually going to be terminated, you just ignore it. You consider it as a no-op instruction. Okay. This is how Intel architectures behave. So in other words, Intel architectures don't have that property. Okay? And so what that also says is, by natively you can't support type 1 virtualization on traditional Intel CPUs. Now there are some extensions that allow you to do it, but until recently you couldn't implement type 1 virtualization. Okay? So now let's try to understand why. Okay, then I'm going to come back and say how they have rectified the problem. Okay, we have like 3-4 minutes. I'm going to talk a little bit and then we'll stop. Okay. Here's a picture that shows type 1 hypervisors. Okay. You have hardware. Okay. You have a type 1 hypervisor running on hardware. There's a virtual machine with a guest operating system. Now, as far as the guest is concerned, it doesn't know it's running on a virtual machine. It thinks it's running on a physical machine. It's totally transparent to the guest. Okay. So now let's take a scenario when that guest was actually running on the CPU, it's not running on a virtualization layer. Okay. So if that guest is running on a CPU, it is the trusted entity. It runs in kernel mode. It can do whatever it wants to do. Okay. The CPU will let it do it. Okay. Which means it can execute kernel mode instructions and everything is good. Okay. So keep that in mind. Now you have an environment where you have a guest operating system that's running on top of a hypervisor. So in this case, the hypervisor is the trusted entity. Hypervisor has taken over the role of what a kernel normally would do. Okay? So it's the hypervisor that's actually running in kernel mode. Everything that's running on top of it is less privileged than the hypervisor itself. Okay? But the guest operating system doesn't know that. It thinks it's running on the CPU directly, a native CPU. So it will try to execute kernel mode instruction as it would normally do because it is the trusted entity. Okay? But since it's no longer running in kernel mode, okay, your Intel architecture will simply ignore all of whatever it's doing because it's saying your user level process. You are trying to execute halt. I won't allow it. I will ignore everything. Okay? So now you have a problem. How do you actually make this work? Because you want to somehow provide an additional level of trust to the OS, but you can't give it all the privileges. You could say run that guest OS also in rings 0 or in kernel mode, but that can cause problems because the only trusted entity is the hypervisor. It needs control. It can't cede control to the guest operating system because there may be more than one of them. There may be 10 different virtual machines running. Do you trust all of them? What if one of them goes and corrupts somebody else's memory? Because if you are trusted, you have complete access to everything, including other operating systems, so virtual machines that may be running. Okay? So you need different levels of trust to make this work. But if you have only user mode and kernel mode, then what's going to happen is anything that the guest does, okay, which is a kernel mode instruction, will not work as is if you ignore those instructions. Okay? But now let's go back to this result, which says, now what if every kernel mode instruction also caused a trap? Okay, let's just take that as a given or an assumption, saying if sensitive instructions are also privileged, then they are going to cause a trap when executed in kernel. So now what is going to happen, if that was true, your guest OS will think it's running on a native CPU. Okay? It may execute some kernel mode instruction on behalf of whatever the user process is trying to do, but those instructions won't be directly executed because you are in user mode, but they will cause a trap. Okay? The trap will actually run an interrupt. Trap is like an interrupt, so that will go to your type 1 hypervisor. Okay? So the type 1 hypervisor will see, okay, the guest is trying to do something. So rather than ignoring it, now the guest is actually, the hypervisor is going to do whatever the guest operating system was trying to do on behalf of the guest. Okay? If you believe the hypervisor thinks you shouldn't be doing it, then you'll say give an error. But in most cases, if you're trying to do the right thing, it will do it on behalf of the guest. Okay? This is how type 1 hypervisors have to work. Okay? The OS, the user level process up there, which are circles, will make a system call. System call will come into the guest. Guest will try to execute some privilege instruction. But you are not running in kernel mode at all. You are actually running in something between a user mode and a kernel mode. You don't have the privilege to actually execute that operation. Only the hypervisor can do it. Okay? So the way you will do it is you will basically cause a trap because the CPU will raise a trap when you try to do it in outside of kernel mode. You will come into, so that trap will bring you into the hypervisor. Hypervisor will say guest OS wants to do something. What is it? You will go into the interrupt handler, execute it, return the results. Okay? The OS will assume that the actual native CPU executed whatever it did, even though it was actually the hypervisor that implemented that functionality for it. Okay? So now you don't need to give complete trust to the guest OS. Okay? Every time the guest OS wants to do something privileged, it's going to cause a trap, so you go do it for me. So that's exactly what you want. You only want the hypervisor to be trusted. The guest OS is less trusted. User applications are never trusted. Okay. So that's your implementation of type 1 hypervisor. So it only works when you have an instruction set that has that property. Okay. What that also means is type 1 hypervisors couldn't run on 3 Intel architectures until they added extra support. So now you have something called Intel VT support, which is virtualization technologies. AMD has something called SVM, which is also extensions to support virtual machines. What these do is that they add a bit vector, right, that you can set. Okay, so if you have, for every instruction you have a bit. If you set the bit, it tells the OS or the CPU saying raise a trap. Okay, so now when your virtual machine loads up, type 1 hypervisor will go and set this bit vector saying, here are all the instructions I can't trust the guest OS to do, but I'm going to set the bit saying if anybody executes it, trap to me and I'll figure out what to do. Okay? So they added this hardware bitmap which tells you flexibly which instruction to trap, and then that is what your type 1 hypervisor will use. Otherwise you will just ignore. Anywhere the bit is not set, you're just going to ignore if you have kernel mode instruction. The idea is every instruction you care about that you don't trust someone else to run, you should set that bit and the hypervisor should go and do the right thing. And so without those extensions, you can't actually implement type 1 hypervisors. Okay? Any questions? We are out of time, so I'm going to stop. All right. So we will continue the discussion, talk about type 2 hypervisors and OS level virtualization next time, but this is just a sort of an initial view into how virtualization at the hardware level works. And we looked at only one so far, which is type 1.